In this example, we're going to use a sign chart for f double prime, so the f double prime number line, to determine intervals where f is concave up or down, and also locations of any inflection points. Concavity and inflection points are the things we read off of the second derivative. And so we need the second derivative to start working through this. So we've been given the original function here. It's a rational function, 1 over the factor 1 plus x squared. And we could take the derivative using the quotient rule here, or realize that this could be rewritten as 1 plus x squared raised to the negative first power, and then we could just get the quick chain rule problem for the first derivative. So that's what I'm going to suggest here. So our first derivative then is going to be bring down the power negative 1, and then we have 1 plus x squared now to the negative 2 because we subtract 1 from the power, and we bring out the derivative of the inside. So the derivative of the inside would be 2x. And so if we could just write this as a quotient now, because we need yet another derivative, and it's probably easier at this point then to use a quotient rule. So let's have the negative from out front and then the 2x factor on top. Push the other factor that's the negative 2 power, push it back down to the bottom and let it be the positive 2 power. And so we've cleaned up f prime at this point, and we're ready to use the quotient rule to find f double prime. Now, not only are we going to need a quotient rule, but we're going to need a chain rule when we're taking the derivative of the bottom there too, so we need to keep that in mind. So for our quotient rule here, we would have the denominator squared, and so that would be the 1 plus x squared. And now instead of raising it to the second power, it would be to the fourth power because it's squared and then squared again. And so then when we clean up, or when we go ahead and take the derivative of the, or when we complete the derivative by putting the quotient rule part on the top here, we have the derivative of the top. So the derivative of the top is negative 2 times the bottom, which is 1 plus x squared, and then we subtract from it the top, which is minus then a negative 2x, times the derivative of the bottom. And it's the derivative of the bottom that needs this chain rule. So we bring down the power 2, we drop the power from 2 to 1, and then we take the derivative of the inside there, and the derivative of the inside is 2x. All right? And so we have a little bit of work to do here to clean this up. So let's take it step by step. We've got this negative 2, I guess this here at the beginning, it's as clean as it can be really. We've got a negative 2 times the 1 plus x squared raised to the second power. But then let's take a look at what follows the negative sign. First and foremost, we've got a minus a negative there. And if we combine everything, go ahead and multiply out everything except for that factor 1 plus x squared, we have a 2x times a 2 times a 2x. So the 2 times 2 times 2 would be an 8. So we've got the plus because of the minus negative, 8. And then we've got that x times x, so it would be x squared. And then we do have that factor 1 plus x squared that we are holding on to. And it's all over the 1 plus x squared raised to the fourth power. So we've made a bit of progress, but we still have two different terms, both of them somewhat ugly, separated by this plus sign right here. This plus sign right there is separating the what comes before and what comes after it as two different terms. So now if we take a look at those two terms separately, we want to go ahead and pull out the greatest common factor that we have for those two terms. And so we see the factor 2 and a factor 8, and so we could see the 2 coming out front. But we also see a 1 plus x squared that's both before and after that plus sign. Two copies of it are before, but only one copy of it is after. And so we're going to pull out one copy, the 1 plus x squared. And then when we do that, what's left over here would be the negative out front of the first term there, because we just pulled out a positive 2, so we've got the negative out front. We have that one remaining copy of the 1 plus x squared. That's what's coming before the plus sign. But then what's coming after the plus sign, if we pulled out a copy of 2, that's 2 times 4 gives us the 8. So we've got the 4 left over there. We still have the x squared left over, and we pulled out the entire 1 plus x squared factor. And so that's what's left behind the plus sign. And then, of course, we can't forget the denominator, 1 plus x squared raised to the 4th power. Now, we've got a couple more things to do to simplify this. We've got a factor of the 1 plus x squared on the top here, 1 copy of it, and we've got 4 copies of it on the bottom. So really we can reduce, and we would have 1 plus x squared now to the 3rd power on the bottom, and that leaves us with just the 2 out front, and we can go ahead and simplify everything that was in the brackets. We've got the distributing of the negative sign, so we've got negative 1 minus x squared, and then we have plus 4x squared in the parentheses there. And so what that leaves us with then is a 2 out front, and then we've got a 4x squared minus 1x squared, so that would be a 3x squared, and then we've got a minus 1. All of that's on top, and we've got the 1 plus x squared raised to the 3rd power on the bottom. So all of that work is simply to get nice factored forms of both the first derivative and the second derivative, and really it's just the second derivative that we need from here on out. So here are those copied over. All of that work just to get the derivatives, but we've gotten them now. And so now what do we do with these derivatives? Well, the question was asking us to find out about intervals of concave up and down and inflection points, and those come from the second derivative. So we need to know where is the second derivative undefined and where is it 0. It's kind of the analogous thing that we did for critical points for the first derivative. So we have f double prime equal to 0 would be where the top is equal to 0. So that would be we've got the 2 equal to 0 gives us nothing. But then we've got the factor 3x squared minus 1 equal to 0. Add over the 1, divide by 3, and we've got x squared equals 1/3. And so then we are going to take the square root of both sides to get what x would equal. And when we take the square root of both sides, we need plus or minus. And of course, we've got to clean up the square root of a fraction would be the square root of the top, which would just be 1, over the square root of the bottom, which we could rationalize to give us root 3 over 3, and of course the plus and minus. So now we've gotten where f double prime is equal to 0, so it remains to see where is f double prime undefined. Well, f double prime is undefined where the denominator is 0. And so we've got 1 plus x squared raised to the 3rd power equal to 0. Well, if we cube root both sides, we're really just looking at the factor 1 plus x squared equal to 0. Subtract over the 1 from both sides, and we've got x squared equals negative 1. Well, x squared for all real numbers x is going to be positive or 0. So it certainly can't be negative 1, so we have no solution there. And so the only places that we need to figure out what's going on at would be the plus and minus root 3 over 3. And so those are going to be the places that we put on our f double prime number line. Since we now have not only the function and the first derivative, but also the second derivative that we're going to be assessing with number lines, highly recommend labeling your number line there with the f double prime. It's indicating that the important points that we put on here came from the second derivative, so the root 3 over 3 plus and minus it. Those are the 2 places that are potential places for inflection points. And we're going to be able to see if those are inflection points by looking to see about the concavity in the intervals that are adjacent to them. So just like before, for the first derivative, we also need test values here in between. And so test values that you could choose that would be fairly easy to plug in would be 0 and plus and minus 1. Those aren't unique test values. You can choose anything that lands in that interval, because using a consequence of the intermediate value theorem, if you pick any test value in the interval, you're going to get the same answer for positive or negative. And so just pick ones that are as easy to plug in as possible. Okay? So now where do we plug in? We've got f prime, and we've got f double prime. Where are we testing these? Well, this number line is labeled f double prime. That is telling us not only are those important points coming from f double prime, but we're putting the test values into f double prime also. And so we're looking here at this rational function for f double prime. The factor 2 that's in front is always positive. There's not even an x to plug in there. But let's take a look at the bottom. 1 plus x squared. Well, no matter what we plug in for x, it's going to be 0 or more. So then, when we have something 0 or more and we add 1 to it, it's going to be 1 or more. So something that's 1 or more that we cube is going to be positive. And so all of these intervals are going to have positive for the denominator. So it really just remains to see what's happening with that 3x squared minus 1 factor. So first we'll plug in our test value of negative 1. When we plug in negative 1, we square it and get positive 1. So we have 3 times positive 1 is 3 minus 1 is 2. So the value is positive. When we plug in 0, we've got 3 times 0 squared, so that's 3 times 0 is 0. And then we subtract 1 from it, giving us the negative. And when we plug in 1, we've got 3 times 1 squared, which is 3 times 1, or 3. Subtract 1, it's still positive 2, so we've got our test values have all been plugged in. And so now we look and see, well, what's happening overall? Well, positive times positive all over a positive is going to be positive. And that happens in 2 of those intervals. The interval that's in the middle is positive times negative on top, so it'll be a negative on top divided by positive. Since there's only one negative, an odd number of negative signs, overall the thing is negative. And so this was looking back at the second derivative, testing into the second derivative, and now we need to make our conclusions based off of the second derivative. So when we see the second derivative positive, we're really looking at something that's concave up. So that happens on 2 intervals. And the one in the middle here, we have f double prime negative, so we're looking at concave down. And so notice that at both root 3 over 3 and negative root 3 over 3, concavity changed. Those 2 values are values that are in the domain of the original function, and concavity changed. And so we do, in fact, have an inflection point at both of those places. And so we're ready to make our final conclusions. We've got concave up. Well, it starts at negative infinity because it's our leftmost interval, and it goes all the way to negative root 3 over 3. We don't include those cutoff places, but it picks back up here at root 3 over 3 and goes on till infinity. So we've got concave up for those 2 intervals, concave down in between. So in between would be from negative root 3 over 3 to positive root 3 over 3. And we've got inflection points at the 2 values, x equals plus and minus root 3 over 3. And so we can make all of those conclusions about the original function based on the second derivative of the function.